try to integrate these.
Yeah, with respect to x?
Same exact function. Let's do it.
Okay, on your mark.
Get set.
Get set, go. Hey! Wait, did we do the same problem?
I don't know. The derivative of this will equal that.
Yeah, and the derivative of this will equal that.
Let's see.
Let's give it a try. All right, so here we go. If I'm taking the derivative of this, we've got the little chain rule action, right? So it's going to be 3 times 1/3, which is 1. X cubed plus 2 squared. X cubed plus 2 squared.
Times the
the derivative of the inside, which is 3x squared. I rest my case. How about yours?
I'm not going to be able to do that so easily.
Well, let's look. So if we take the derivative of this guy, that's going to be 3x to the 8th.
Okay, yeah, that's good.
12x to the 5th. 12x squared. Derivative of c is 0. Okay, but where in the heck did this come from?
Well, I thought the only way we can integrate is if we turn into a basic polynomial.
Beautiful.
So then we could do the whole add 1, divide, and
Yeah, okay, so you expanded this
turned it into a
out.
basic polynomial. And
You did the double distribution. You did that looks beautiful. Well, I'm pretty sure these are the same. How? Let's turn this into this, shall we?
that we should.
Yeah, okay, so x cubed plus 2 to the 3rd, using our little,
X cubed plus 2. Do you want to use Pascal's triangle
let's
here?
use Pascal's triangle.
Really?
I love it.
Yeah?
Yeah, why not?
Okay,
Okay, so we
X
have
cubed every time.
Cubed plus
3
x cubed squared.
Plus 3 of 2 of these. And
Plus 1.
1 of these.
Okay, so it's x to the 9th. X to the 6th.
That's a 4. And then you have a third of that.
Third of that. 1/3 x to the 9th.
One-third times 8, I'll call a constant.
We'll call that a constant. Hey, it's the same thing.
All right.
Okay, but hold on. How did you call that 8 a constant if that's a constant?
Well, a constant plus constant.
It's another
Still a
constant. So we
All
can
right,
just
so
call it a c. All
They
right.
look different. They have the same general. Well, I mean, they have the same variables, and that's all good. Same
And we know that
exponents.
this is an x to the 9th. That's an x to the 9th. Yeah.
But you were done way before me.
I was done way before you.
That probably has.
Yeah. This is a
Oh.
cool strategy that we sometimes, I don't know where they came up with this name, but they call this u-substitution. Where do you
I've
suppose
sometimes
they came up with that?
heard it called just change of variables.
Oh.
So it might not matter that you use a u,
It doesn't.
because it seems what's happening here is actually you've taken a single variable, so a monomial, and made it stand for a more complicated piece of the problem.
Yeah.
And I think what worked out nicely here is the derivative of your step, your derivative of u, was the leftover pieces. Right? 3x
Yeah.
squared
Yeah.
px.
And that's how I designed it. I looked at this and I thought, that looks like the result of a chain rule. If I had a function and I was taking the derivative of that, I would use the chain rule. So if I'm taking the antiderivative, I'm seeing, oh, there's some chain rule there. I want to
Oh.
undo a chain rule. So I thought, all right, I'm going to look at the more complicated part of this.
The piece that would need its chain, really.
Yeah, and say, okay, well, what's if I were taking the derivative of this, what would the chain rule give me? It'd give me the 3x squared. So I'm going to let u stand for that part. So when I take the derivative, those pieces stand for those. It's really a handy strategy.
One question about maybe what happened in between these two steps.
Yeah.
Is it that we've taken the derivative implicitly with respect to x? So I almost am thinking that in between here may have said the derivative of u with respect to x is 3x squared dx dx. Right? We don't really write this as a 1, and then you just cross multiply.
That's right.
Is that what happened there?
Yeah.
So it was really the derivative of u with respect to x.
And this is one of those weird things where du dx is sometimes used as a label, and now we're kind of doing something algebraic with it. It's a little weird, a little uncomfortable, but yes, you can think about it that way as well. Absolutely.
I like that process. Let's call it u-substitution.
We often call it u-substitution. Should we do some more?
Well, does it always work out so perfectly?
No. It works just for some functions that either involve the chain rule or for some other functions when you can kind of...
Yeah, I like to think about it that way too. You mentioned it before. We're not taking this thing's derivative. But if we were to, and we were to need the chain rule, that's when u-substitution comes into play.
Exactly right. You know what? There are tons of very straightforward functions that do not have straightforward antiderivatives.
Yes, there are.
In fact, there are probably more functions that do not have antiderivatives than do, if you want to think about that. But there are many functions, and we can find the antiderivative nicely, or the indefinite integral, by using this cool strategy.